In this video, we're going to learn about operations with vectors. Operations with vectors. The first operation that we're going to define is the sum or the addition. So let's suppose that we have a vector and we have the component form of this vector, A, B. We have another vector, V, and the component form will be C and D. Okay. We can define the addition of these vectors, so U plus B, just by adding the corresponding components. That means I will add the horizontal component of both, A plus C, so the horizontal component, and I'm going to add the vertical component, so B plus D on each one. Doing this, I will get a new vector, right? The vector defined by U plus B. The subtraction, what about the subtraction? If I want to subtract these two vectors, vector U minus vector V, is basically the same idea. I will just subtract the corresponding components. So A minus C, and B minus D, And that's all. That's how you add or subtract vectors. Let's do a couple of, actually we can define the multiplication of a vector by a scalar, and then we can do the examples. So if we want to multiply a scalar, let's call it S, by the vector U, the only thing that we need to do is just multiply that scalar by each of the components. So S multiply by AB will be S times A, S times B. Okay, so that's the whole thing. That's how you add, subtract, or multiply by a scalar. So let's do a couple of examples. Let's suppose that we have these vectors. So we have vector U, that is -2, 1. Vector V, that is 5 and -7. So what if we subtract the vectors? So what if we do vector V minus vector U? So since it's V minus U, it will be 5, it will be like this, right? 5 minus 2 and -7 minus 1. So negative times a negative is a positive, so 5 plus 2 will be 7. -7 minus 1, it's -8, right? So the new vector subtracting that we get by subtracting vector V and vector U will be this. Okay, let's do another one. Let's suppose that we want to add 2 times U. Let's combine the problems. 2 times U plus vector V. Okay, so what we have here is 2 times U, that is this, right? -2 and 1, plus vector V, that is this, 5 and -7. Now, we know that this is multiplication by a scalar, so we just multiply each component by that number. So 2 times -2 is -4, 2 times 1 is 2, plus 5 and -7. And the only thing that we need to do now is just add the components. So -4 plus 5 will be 1, right? Different signs you subtract, 5 minus 1, and you leave the sign of the greater number. And 2 plus -7 will be 2 minus 7, that is -5. So this will be our result if we add 2 times vector U plus vector V. We can do another example. Let's suppose that we have in unit form. Let's suppose that we have vector M. It's equal to 2i plus j. And we have vector N that is equal to -i minus 5j. All right, so let's do a problem. Let's suppose that we're trying to, let's just simply add M plus N. If we're adding these two vectors, remember that the components, if you remember what we learned in the previous video, this 2i and this -i are actually the horizontal component of each of the vectors. I mean, you can rewrite this in component form as -1 and -5 if you want. You can do the same thing here, 2 and 1. because to write it in unit vector form, the only thing that you do is take the component and multiply by I, the horizontal component by I, and the vertical component by J. So we can do it like that. All right, so M plus N then will be 2 plus -1, that is 1, and 1 minus 5, that is -4. That will be your new vector. Can we rewrite this in this form? Yes, we can. So 1 times I, that is actually I, plus -4. So -4j. That will be the sum of the vector in the unit form. And that's it. That's how you add or subtract vectoring in those two forms. We can define a new operation that is called the dot product. The dot product. So the dot product of two vectors. So again, if we have vector u, we're going to multiply by vector v. It's going to be equal. So let's write it in component form. If we have a b times cd. So basically, what we're going to do is just multiply the corresponding component. So a times c added to the multiplication of the other two components, the vertical components. So b times d. Notice that when we do this, this is not a vector anymore. This is a scalar. Okay? So that's how you apply the dot product of a vector. Let's do an example. Let's suppose that we have vector u equal to 3 and -2. And we have vector v equal to 4 and 5. Okay, so if we multiply u, or the dot product of u and v, then again will be the multiplication of the corresponding components, so 3 times 4, plus the multiplication of the vertical components, so -2 plus 5. 3 times 4 is 12. -2 times 5 is -10, so it will be -10. And 12 minus 10 will be 2. So the dot product of these two vectors will be +2. Okay. What if we do it in the unit form and see how it goes? Let's suppose that we have u equal to -3i plus j, and we have that v, it's equal to -4i minus 6j. Okay, again, if you want to rewrite it, it's fine. If not, you can do it like that. But if you want to see it in component form, remember that this is basically -3 and 1, and this is basically -4 and -6. Okay, those are the two vectors. So if we apply the dot product between these two vectors, then it will be -3 times -4 plus 1 times -6. -3 times -4 will be positive because negative times a negative is going to be positive. 3 times 4 is 12. 1 times -6, -6 times a positive, it will be -6, and 12 minus 6 will be 6. So the dot product of u and v is going to be scalar 6. Okay, so that's all. That's the only thing that you need to do. Do you need to rewrite this in component form? No, you don't. Remember that you have the numbers right there, so you just use them. I just want to do it in this video so you can see and you can remember how to do it. The dot product has all the properties that you know from the multiplication. That means that if you multiply u or apply the dot product of u and v, it's going to be exactly the same as b times u, or b dot u. If you have the dot product of a vector and the addition of two vectors, then you will have like the distributive, the usual distributive properties. It will be w dot u plus w dot v. Okay. The same goes with the associative property and so on. Okay. We also have something that is called the dot product theorem. So the dot product theorem. We're not going to prove this we're just going to use the result. Okay, so turns out that if you have the angle in between two vectors, so let's suppose that we have two vectors, all right? So our first vector go this way and our second vector go this way, okay? And we have the angle in between those vectors. So we have that angle theta. Okay, this is vector v, this is vector u. Then the dot product of u dot v will be equal to the multiplication of their magnitudes. So the multiplication of magnitude u times magnitude v times cosine of that angle in between them. Okay, so, and that is a new interesting result. Notice that you have a triangle here, and you can easily prove that applying the law of cosines, since you will have side angle side, you can prove that this is actually a thing. Also, from this result, we can get the angle between two vectors. How can we do this? Well, if theta is the angle in between two non-zero vectors, that means that they have magnitudes like this, then cosine of theta is going to be equal to the dot product u dot v of the two vectors divided by their magnitudes. So if we have this information, we can have, or we can find the angle in between the two vectors. Okay, so let's do an example of this. Let's find the angle in between the next two vectors. So we have u equal to 2, 5, and we have vector v that is equal to 4 and negative 3. Okay, so let's find the angle. So notice that the formula was cosine of theta equal the dot product in between these two vectors. So 2 times 4 plus 5 times negative 3, 5 times negative 3. So we multiply corresponding components, remember that. And we're going to divide this by the multiplication of their magnitudes. So what would be the magnitude of u? So let's look for that up here real quick. Magnitude of u is going to be the square root of 2 squared, that is 4, plus 5 squared, that will be 25. Right? So this is square root of 29. All right? And the magnitude of v is going to be the square root of 4 squared, that is 16, plus negative 3 squared, that is 9. So this is square root of 25, that is 5. Okay, so we have our magnitude. So we multiply 5 times square root of 29. 2 times 4 is 8. 5 times negative 3 is negative 15. A minus 15, it's negative 7 over 5 and the square root of 29. All right, so let's do this operation in the calculator. So it will be negative 7 divided by 5 times square root of 29. Let's close that, and we get that this is negative 0.259. Let's use just straight decimal. So theta is going to be cosine inverse or arc cosine of negative 0.259. Okay, and this will be equal to arc cosine of negative 0.259. This is 105.01 degrees. 105.01 degrees. So actually, it's basically 105 degrees in between those two vectors. So the angle in between those two vectors is 105 degrees. One of the interesting results that we get from the dot product is that if the dot product of two vectors is 0, then we know that the vectors are orthogonal. That means that they are perpendicular. So what we have is this. If the dot product of two vectors is equal to 0, then vector u is going to be perpendicular to vector v. Okay, that it's called orthogonal. The vectors are orthogonal. If they're not, then they're neither orthogonal or perpendicular. And another result is if one vector is equal to a scalar and the other vector, that means a multiple, then vector u, it's parallel to vector v. That's another pretty interesting result. We can check this with a couple of examples. So I guess if we have, let's suppose that we have that vector u, it's equal to 2 and 1, and vector v, it's equal to -1 and 2. Right? So the only thing that we need to do to check perpendicularity or if they are parallel, then it's to apply the dot product. So u dot v is going to be equal to 2 times -1, that is -2, plus 1 times 2, that is 2, and -2 plus 2 is 0. So since the dot product is 0, then they are perpendicular. Vector u, it's perpendicular to vector v, okay, from these two vectors, right? We can do another example. Let's suppose that you have that vector m, it's equal to 2 times -10, and vector n, it's equal to 1 and -5. Okay, so we can check for perpendicularity. So vector m dot vector n will be equal to 2 times 1, that is 2, and plus, remember, -10 times -5, that is positive 50. So plus 50, and this is 52. So since it's not 0, they're not perpendicular, Now, maybe they are parallel. How can we tell? Okay, notice that to check for parallelism, vector 2, 10, can be written in terms of vector n, because we can say that this vector, multiply by 2, by the scalar 2, is exactly the same as having this vector, right? It's exactly the same thing, because 2 times 1 will be 2, 2 times -5 will be -10. So since vector m is equal to 2 times vector n, then they're parallel. All right, so the two vectors are parallel. M, it's parallel to vector n. I think we cover all the topics that we were missing from the class, from the previous videos. And in the last video, we're going to discuss a couple of problems related to vectors. So see you in the next one.